So in this video we're going to look at the proof of our centripetal acceleration being w squared or v squared over r. I know you Greek guys will be saying omega. So let's have a look. So we look at w being our angular speed. T will be time in this question, in all questions. T will be time, and the angle opened in the circle after t seconds will be Wt. And we know that any point on our circle will be the radius by the cos of the angle in the I direction plus the radius by the sine of the angle. I'll put the angle in brackets for this proof. In the j direction, this will be my displacement of my particle at any time. So back to our earlier topics, s is equal to ut plus a half at squared displacement. If we differentiate displacement, the s dt is equal to u plus at, which you guys know is velocity. So the s dt will be velocity. Let's see what it becomes. So if we differentiate cos, we get minus sine. I'm just going to jot these down. Cos goes to minus sine and sine goes to cos. So differentiating or cos wt, or is a constant, so we're going to get minus or sine wt, and we differentiate the angle with respect to t, we're going to get w. And then if we differentiate sine, we're going to get cos, so that will be plus or cos wt. Differentiate wt, we get w. So tidying this up, we're going to get minus w or w, it doesn't really matter, sine wt plus w or cos wt. So this is my velocity. What happens if we differentiate velocity? If v is equal to u plus at, dv dt, differentiating velocity will give me acceleration, which is what we're looking for in this question. So this is my velocity. So dv dt will become, differentiating sine, we get cos, so this is going to be minus w or cos wt by the differentiated angle, and then cos goes to minus sine, so we're going to get minus w or sine wt by the differentiated angle with respect to t, which will be w. So dv dt becomes minus w squared or cos wt minus w squared or sine wt. So if we tidy this, dv dt, which is my acceleration is going to be, I could factor out w squared r, but I'm going to bring it back to displacement from the beginning, which was this guy. So I'm going to leave the r in and see can we get something in terms of s. So a is equal to minus angular speed squared times or cos omega t plus or sine omega t, which is equal to minus w squared by displacement. So we can see here that acceleration, therefore a is directed along displacement, along s, but in the opposite direction, which is towards the center. So now let's look at the magnitude of this acceleration. So the magnitude of A should probably be consistent with my arrows, is equal to, okay, what have we got? We have, well, I'll take this whole expression here. It's going to be the square root of everything squared added together. So it's w squared squared is w to the power of 4 or squared cos squared wt plus similarly w to the power of 4 or squared sine wt. Sine squared wt even. So if we factor out cos squared plus sine squared, or factor out w to the power of 4 or squared, we'll end up with cos squared plus sine squared, which is equal to 1. So we're going to get the square root of w to the power of 4 or to the power of 2, which becomes w squared or. So this is the magnitude of my acceleration, w squared or. We know some other information about this too. We know that w is equal to the velocity over r from a previous video. So we can have w squared or v over r to be squared times r, which is equal to v squared r over r squared, be careful, which is equal to v squared over r. So these are my accelerations, my centripetal accelerations. When force is equal to mass times acceleration, the force here is going to be m omega squared or m v squared over r.